So let's look at some physical application of integral. Talking about the applications in physics right here. Application. Here specifically, we want to focus on the kind of proper calculating work. You guys have done some basic physics class, right? Some basic tasks, some basic physics understanding. So here's the idea right here. Well, work, no matter how fancy the stuff we go about to go through in the next few examples, but you guys have to always stay focused in this one fundamental from physics right here. Work, right? Well, it's the amount of energy, correct? It's the amount of energy that you spend out to do some action. See what I'm saying? So we measure that in terms of what? In terms of how much force we're exerting on the distance. So force times distance here, that's work. Because you see, I need force to either drag, right? Or pull. See what I'm saying now? Okay. So force right here, drag or pull. I mean force, well, the drag or the pull is already because the object got a mass, right? And the drag or pull is in whichever direction there's acceleration rate like that. So that's why you guys famously heard about force equals m times a, right? Mass times the acceleration of the object. You need to exert some force, right, to make that accelerate. See what I'm saying? Going from rest to a certain speed, like that, I mean accelerating. But then, how far you drag that thing, right? How far you bring that thing. That's why it's, the amount of force you're exerting on that object, and then you need to drag it a certain distance, and that becomes your work. See what I'm saying? The amount of energy that you spend out. Because otherwise, I mean, a lot of times your physics instructor has this famous experience. I'm not sure if he has done that at the high school, but they have some kind of surface that they have little air that they keep blowing into the object to keep it flow and it can move without friction. Because right now on the floor there's friction all over. So in any physics lab, the instructor has some kind of tools that they got kind of like a flat surface with a whole bunch of with millions of little holes that they blow airs up so that any object you put there is kind of floating. So that the mass is still there, right? But the gravity is still pulling, but you don't have friction. So you can, when you just easily push that, right? That's reflected through as amount of force that you need. You push that thing going. You know what I'm saying? To make that thing accelerated. Because right now it feels hard to push it because there's that roughness on the floor, the friction on the floor, and it's not telling the true story. See what I'm saying now? And so, but in the end, so work here is how much force you exert on an object to move that a certain distance. So it's a product between the amount of force and distance. So just that, right? So now think about life is not always simple. In physics, in basic physics, we just do one straight path, right? And we're talking about equal force. We're talking about a lot of time in physics. We're talking about equal force and constant force everywhere, right? That's what we do in physics, constant force. Right? Along the distance d like that. That's what we do in physics. But now think about you guys are doing a little more advanced stuff like that. Think about that when you just started, right, you got some good amount of force, big amount of force, and then as things already move on, I mean, it's the way how it is. When you first started, right, you have to push hard to overcome that friction. See what I'm saying? Huh? But then as that thing already started moving, right, it's easier, and then when you kind of like feel like you already got into some good grip of that, right, you don't have to spend as much force. So what I'm trying to demonstrate now is that force can actually vary depending at different instances where you're pushing that thing with that. So we're no longer, so in physics, a lot of times to keep the problem simple, you guys, at your level, you learn about doing constant force, right, along the way, but think about in a more advanced situation, force is changing. The amount of the force that you're pushing is changing. And so in that way, just like still on a straight path from a point A to a point B, right? You see, we can call that anywhere here as an X point, right? But the force at this point is different with the force at this point, for example. So the force here, you can call it as a function. It's a force. It can be measured as a function of the x distance away from that starting point. And then so same way right here, the force becomes a different value when it gets a further x, for example. That's why I'm saying We got a varying force, no longer a constant force. But so, how do we calculate work? No matter what, a little bit of change from the one point to another next point again, we've got a small distance, right? From any point to another next point, you've got a small distance. That's a distance d again, but then it's so small enough that you can call it it's a dx change again. See what I'm saying? Also, the dx is kind of like represent a location, so a small change in location, right? It's a little distance. You guys following? And so with your force being now a varying amount, right? At any infinitesimally small, that's still a small change in distance. And so the force at that point, because the interval of the change in distance is so small to the point that the force at the beginning point and the force at the end point makes no difference. So it's just the same as the force amount right at that instant. So force multiplied with how far the distance you have gone. See what I'm saying now? Or in another way of seeing it, So all that here, another way people can explain that, it's still the force times. Another way of seeing it is, see, force here, okay? Actually, what I explained earlier does not reflect what's in the picture, but let's say from your starting point, right? The x distance is here. See what I'm saying? Huh? And then to another x distance. To another x distance. So the force from here to here, the amount of work from here to here is some f, right? So f of x times the distance. And from here to here, it's another f of x times some distance x. From the starting point of that, then the change, a little change, see, everywhere from you moving from one point to another point, there's a small change in x. So it's small because there's an x here, and then there's an x here. You guys see that in my picture right there? There's very small change in x, right? But it makes some changing. So the force multiplied with the dx gives you just a little amount of work. That's called a dw. Okay. So it's just a little work amount. Okay. That's what f dx is for. And so now we're accumulating. So all of those work again on the dw, right? The little work amount in each of the infinitesimally small amount of work accumulating from some stars, some end, right? And so that formula will get you the total work when we push an object along a path. So from some edge, still stick with it. Same tradition, we're accumulating all of the little work amount from start to end, but all of those are fx times d dx. Okay. That's the fundamental, that's the accumulation of all little work. W, okay, a little amount of work. There's another situation I can describe. We will get to that problem later on, but think about there's a person, right? Think about when I was talking about the varying force, right? The non-constant force. And think about there's a person, okay, and he was pushing a crate, like a heavily loaded crate, right? Lots of motors in there. See what I'm saying now? So very heavy, he has to spend a lot of energy to push it. But then along the way, there's a good friend, right? Along the way, there's a good friend that's in some amount. The friends continuously take away a piece of powder, put it out. So the crates get lighter and lighter along the way. See what I'm saying now? And so of course, as the crate gets lighter, right, then he has to spend less force as he moves on. See what I'm saying now? That's what I mean by varying force. But by the time that he gets here, maybe the 3 motors has been removed, right? See what I mean? So the crates only become just something like this, right? With a lot lighter weight. Okay. So by the time the person gets here, right, it's it's going to be a lot less force, right, compared to that. So just a small change, right, a little bit of small change, the distance from here to here, some distance you want, right, and then the amount of force from there to there, right, maybe some amount of force F1 times d1, and then from that point, right, to another point right here, this d2, oops, there's some change in the force, right, so that's why it's an F2 times d2. We have to sum up all of the little forces. So these right here is the change in the distance, the change in the location, right? And that's represented by the infinitesimally small amount of work. Means small amount of distance. So force times those little distance. Each one of these is a little work amount. So we're summing up all of those, right? That's what we're adding up. We get the total work. And of course, see, we keep adding more in because the total road is long, right? The total path is long. So we're going through a lot of instances, not just only a few of the discrete distance like that. You know what I'm saying? That's the kind of problem. Okay. All right. And so in that one, with that fundamental, it's enough to drive into a lot of problems already. So let me take you guys into an example over here. You will experience that. So let's look at this problem right here. You can go ahead and spend some time writing it down. So, in this problem is admittedly just to get you comfortable with the idea of we having varying force. Okay. So it's not much to question about how the force was derived. So here we've got a varying force, the counter force, right? Being 3x cubed plus 3. Just think about on the x-axis here, you got a particle, right? And then in order to move that particle from the origin to x equals 9. So origin is here. Right? X equals 9 is somewhere out here, so you got a path, right? You got a pathway like that. So at every x along the way here, the amount of force you need right there at that instant, right, is going to be 3x cubed plus 3. You can put away the question of how did physicists come up with that function. That's why you need to take a physics course, right? Because you do experiments, you go to your lab and then you come up with the approximation techniques and all that, right? You come up with a force function. But the idea now for this problem, our purpose here is just to take that force as something already given. But what we need to realize is a varying force, right? And then at every x instance, right, you got a different force amount. And that's why now to calculate the total of work, see, think about it as a crate, right? The force to push that crate from this point 0, okay, from the origin x equals 0 to x equals 9, you got varying force, right? All right. And so in that way right here, we want to calculate the total work. So all you have to do is set up right here force as x cubed plus 3, right? Multiply with every infinitesimally small change in distance, right? Because from this x to the next x right here, you guys see what I'm saying now? And with my pencil stroke, I have to make that some distinguishable distance dx, okay, but it's supposed to be infinitesimally small. See what I mean? Right? So you got x, right? And then you got a small dx. Yeah, see what I'm saying now? So that when it gets so small, right, the x in that interval makes no difference to any one of the two endpoints there. That's why the force can just be defined to be a function at that x, and then we multiply with the x. And that's the dw, right? The little work amount here. We're accumulating all of that. Where's the starting point? X equals 0, right? Yeah? It would be 3x cubed plus 3. You're right. Thank you for that correction. X cubed plus 3. Right? And then we're accumulating all of that from 0 to 9. Okay. So I want you guys to get into that habit to keep understanding, because here, in a class setting like this, I don't have much time to explain too much, but again, keep thinking of this as a dw over here, right? It's a little, that dw represents a little amount, right? Little amount of work. Work is always the force times the distance, right? Some small, infinitesimally small distance you get. So now we're ready for calculating the total work. Using integrals to calculate work is one of the fascinating applications like that. So now it's just the usual thing right here. We've got a 3/4 x to the 4th, right? Plus 3x. And you guys follow it? Right. then the interval is, this antiderivative is going to be evaluated from 0 to 9, right? Go ahead and help me out with that final calculation with that. And yes, well, the good news, we have the low end being a 0, right? Yes, did I miss something?
Would you not be multiplying it by x?
No, just that. Which one by x, though?
The dw.
The dw?
Yeah.
I mean, the whole thing here is already a dw.
Well,
So it's a force right here, a varying force, right? We multiply with a small, infinitesimally small change in distance. That's enough for that. And we're accumulating all of that. So we don't need to multiply with an x. Because the x is just a point along that path that's responsible for the changing force amount right there. Yes, that should be, as writing it down, meanwhile I'm waiting for you guys to do the calculation time. Force times 3 force, right? And force is 3 times 9, do you guys agree? Right. And then we'll go ahead and do that work for you.
4,947.
4,947?
Yeah. 0.75.
0.75. Okay. So you got the decimal, but that's okay, that's precisely that. Guys, it's work. So what's the units for work? The standard one. Oh, I can remind you. Joules. Okay. So, time these are standard 175 joules. Okay. It's actually Newton's times meter because it talks about the amount of force, right, to move that in a certain distance. The amount of force responsible for some distance. So it's not per meter, but it's actually Newton's times meter, right? And that's the that's why joules came in and kind of come up with a new unit again. Right? So that's work. And so this problem here is just a straightforward problem. Hey, you got a function that represented your force, your varying force, right? But now let me tell you, these kind of functions do exist out there. These functions do exist out there. So this problem may be just something that for us to work directly. But you may still wonder in your mind, I mean, where do you see functions like this? On one straight path, right? And then your force is different depending on where that x value is. Let me now take you guys into the next problem right here. You guys ever observe how a spring works?
Yes.
Yeah, I mean, so that's the idea, and it also depends on the material that where the spring is made, okay? See what I'm saying? There's a steel spring that's extremely hard to stretch it or compress it, right? Or a rubber spring is so easy, you see what I'm saying? But it's all the concept of the spring like that. So really, there's a physicist. And this law is named after him. It's called Hooke's law right here. I forgot what his complete name was. That was the last name of the physicist. He come up with, think about the spring like this. The situation is you hang one end of the spring here, right? So there's always any spring has its own natural length, right? The length that's without stretching or without compressing. So this is called the natural length of the spring. And then the spring can be the whatever material. It could be steel spring, iron spring, or rubber spring, or the plastic spring, whatever. Okay, I haven't seen any wooden spring yet. But anyway, so from the natural length, if you stretch that x distance, see what I'm saying now? From the natural length here, you're stretching it out x distance, right? Or you're compressing it x distance. See what I mean? Okay. Hooke's law proven. So that takes you back because if you the force to stretch the spring from the natural length, the force to stretch that x distance, the force you need for that is going to be K x. It's a varying force again. See, it depends on how far you want to stretch it. See what I mean? So if you want to stretch it only like that little distance, right, then you need little force. But you need to stretch it really far, right? You need a lot of forces. And so you can feel it as you keep stretching, as your distance continuously changing, right? Then you keep continuously exerting different amount of force at every instant that you're moving along the way again. See what I'm saying now? Right? So Hooke's law, that physicist, right, came up with this law here. He has proven it, right? And now in these modern day we have become Hooke's law. So what exactly is a K here? K is called the spring constant. Spring constant. So every spring has a different spring constant, right? Because the material of the spring is what determines that. See what I'm saying? Huh? If it's a steel spring, or if it's a what is it? What have I been saying? The rubber spring, right? It's all having different spring material. See what I'm saying? Now, that's why it's all resulting in different spring constants. But in general, Hooke's law say that the force that needs to stretch or compress at x distance away, right? I'm talking about the absolute x distance away from the natural length. That's going to be kx. You guys with me? Okay. And so now back to the question itself right here, the information we have it. So just think of it this way a little bit. For now, at this starting point, we don't know the total amount of work. I mean, we want to calculate the total amount of work, because that's what the question is asking. Find the, right here. We want to calculate, right, how much work, right, in foot-pound here is done in stretching the spring from natural length to 8 feet beyond its natural length. See what I'm saying? Huh? Right, so that means as far as the setting up of the problem, here's how we're setting it up. How much work? Okay, we're calculating work, so work to stretch that. So at any x value, we're looking at any x value, we're exerting an amount of force being kx. But then with that amount of force, we multiply with the small amount of this change in distance, right? Small amount of change in distance. And we're accumulating all those little work amount from 0 to what? Because 0 means a natural length. And then being 0.8 feet away. That's our setting up point there to get the total work. You guys see what I mean? Right. So that's one way how we're approaching that. But you're starting to feel some danger in the sense that we don't know the K value, right? We don't know the K value here. You guys following? Okay, so let's keep it there for now. So as far as the integral, the K here is playing in the role of a constant coefficient. We can put it out front, right? And then your integral remains 0 to 0.8 here, x dx. So that means we're looking at a k over 2 x squared, right? Evaluating from 0 to 0.8. Are we good with that, okay? Okay. And then that means we're looking at 0.8 squared over 2 times k, right? And then substituting in the 0, making it all 0 out. So in the end, you're still stuck with a k value. Are we good with that? Okay? But this is the general work, how we calculating that work amount, that total work amount. Okay? But now, how do we figure out how much k? I mean, what's the k value? Because we don't see the information. The problem did not give you any information about what kind of material is this spring. And believe me, even if you know the material, it's still you're gonna have to hop onto the internet and search for reference, right? Hey, steel spring, and there's a composite steel and different kind of steel as well, right? And come up with different the spring constant. So we don't want to do things like that. So here's the trick. And by the way, 0.8 squared, 8 over 10 squared, that's making it the 64 over 100, right? So 0.64, 0.8 squared is a 0.64, correct? Right? And over 2 is going to be altogether is a 0.32 k. So like I said, we got some work around, but we're still stuck with that k. Okay. You guys okay with me on that again? So now here's the thing. We're gonna dive back into the problem and we identify some more, and we can identify some more information. On the problem it says we need a force of 5 pounds, right? A force of 5 pounds is required to hold a spring to stretch 3 feet beyond its natural length. You guys see that there? Valuable information, and that's actually the way how we're doing it. A lot of time with lab, it's theoretic. So you go in the lab and you can say they have a device to measure how much force actually in any of physics lab. Right? They have a device like that. So in the way how I see it, think about this. According to that description, a force of 5 pounds, right, is required to hold a spring that stretches 0.3 feet beyond its natural length, right? So that means what? F of 0.3. See what I'm saying now? 0.3 feet beyond its natural length, right? F of 0.3 equals 5. You guys agree? The amount of force, right, to stretch that 0.3 feet beyond natural length is 5 pounds. But then on the other hand, according to Hooke's law, right, on the other hand, F of 0.3 must equal what? According to Hooke's law, 0.3 times K. You guys follow me? This is known information right from the experiment, right? And this is according to Hooke's law. If you want to stretch that spring 0.3 feet, longer or beyond its natural length, right? And you need to exert a force being theoretically 0.3 times K. So we're gonna set these two equal. We're gonna equate these. So we're looking at K, or from these two known pieces of information, right? We're gonna lead to setting up an equation: 0.3 K equals 5. You guys repeat that? Okay. And so K, now we now have access to finding out what K is. K is 5 divided by a 0.3, right? And a 0.3 is like a 3 over 10, so making it like a 50 over 3, right? Something like that, right? K is about a 50 over 3. Agree? So now all of a sudden we realize, hey, coming back to this work, we're ready for calculating that total amount of work. So work equals 0.32, right? Times with K value being a 50 over 3, yeah, and then we do the overall calculation. You guys can feel free to give me the final answer in decimal. All right, anyone? Yeah?
16/3 foot-pound.
60/3 foot-pound, right? 60/3 is like a 5 point something.
5 for your feet.
Very good. Thank you for that. 60/3, right? Pounds. So FT pounds. See, this is foot pounds, but it's not foot per pound, right? It's how much force to move that amount of mass there. All right.